Today we are going to start with lecture 4, which is about volume studies, and this has been taken from chapter 10 of the textbook. First of all, a review of some of the terms which we have already studied in this course. Volume, which is the number of vehicles per day or per hour going through a point or a segment or a direction of the highway. Rate of flow is the flow which is taken for less than 1 hour and then converted to a per hour rate. That is called rate of flow. Then we have demand, which means the number of vehicles that are required or that need to go through the highway. Then we have capacity, then the maximum number of vehicles which can be handled by a segment of the highway. All of them can be represented in vehicles per hour or passenger cars per hour and per lane as well. And the main feature here is the demand. Demand can change the rest of the things. Even the capacity is designed according to the demand. And among these factors, only capacity is the one which is constant. Okay, so we said demand changes everything. And the demand by itself changes according to time of the day of the week. It can change in different months and seasons. So for example, demand in the morning time is different, evening time is different. Demand on weekends and weekdays is different. Demand in, let me give you a very obvious example. In Muslim countries, Ramadan is completely different season from the rest of the year. You will see a drastic change in the demand. And demand can change because of events as well. So you have Formula One in Bahrain, you have national days, and you may have an accident on the road, some construction activity going on, or some extreme weather events like very heavy rain or fog or snow. They can also change the demand. So to manage this demand, we need to know the real-time characteristics of the traffic, and then the management should be according to that. So the system which is employed for this purpose is called ITS, Intelligent Transportation Systems. So these systems are those which collect real-time traffic data, and that data is transferred to the control center and or to the traffic devices which are employed on the road. So one example is the signals which are connected with sensors, or the speed signs which are changeable, like electronic signs. A big part of this ITS is driver awareness, because we want to reduce the load of management on the traffic authority, and so we give the driver a chance to avoid the problem from the start. So you tell the driver there's going to be there's an accident somewhere, so he can avoid the road. There's an extreme traffic jam or some road is blocked. So you tell the driver in advance so that he can decide accordingly. These are some of the figures taken from real data, which gives you an idea about the changes in demand. So first of all, you can see these pictures or these graphs. The trends in them are different from each other, and they are different because of the location. You can see each graph is for a different type of highway or different location. Then in each graph you see different curves, and these curves again at many points these curves are far from each other. So you can see it here, so you can see it here. Okay, so what are these different curves representing? These are representing different days of the week, and two of them are weekdays according to US. So you can see that even between the weekends, two of them are weekends, sorry. So even between the weekends, there can be a change in traffic pattern. And then you can see the graphs. For example, to take this one, almost goes from 0, can go up to as high as 12,000. So 12 times increase in the traffic, okay, in the same day. And this is according to time. So now you can fully comprehend the need of a real-time traffic management system, and you can see how complicated are the changes in demand. Okay, then we have intersection volume studies. Now before that we have talked about volume studies done on segments in the previous lectures. Now we will go up a bit higher to a bit higher level, and we will talk about intersection volume studies. So they are also called as turning movement counts or TMCs. They are done manually to have the accuracy because if you're doing it through sensors, then sensors can tell you how many vehicles passed in front of them or over them, but they cannot tell you which way they are going, and especially where the lanes are shared. You have one lane from which you can go in different directions. So that's why we prefer to do manual counts. You can use video image processing as well for this task, but then it will require a lot of calibration. You have to train the system, the software, so that it can differentiate between different turning movements. Okay, so if we are relying on the manual counting, then you have to take care of the observers. You have to place the observers from which their visibility to the uh, assigned movement is easier. So somebody is assigned the left turning or the U turning, then he should be maybe in the median, on the median, okay, or somewhere from where he can see the movement unobstructed. And another thing is you have to keep in mind that the volumes are counted when they are leaving the intersection, meaning crossing the stop line, and we call it departure volume. Another thing you have to keep in mind is the experience, the skill of the observers. All observers will not be at the same level of skill and experience. So we divide the movements into major and minor. Major has more volume, minor has less volume. So in an experienced observer can be assigned one or two minor movements, but the major movements should be assigned to more experienced observers. To increase the accuracy level, you may go towards a lane-wise approach where one observer is counting volume from one lane at a time. So you just have to worry about one vehicle going at a time. But then you have to also keep in mind that how many observers you will need in that case. And another thing which is for manual counting is the brakes. The manual counting requires brakes, alternative brakes or brakes within the counting period that we have discussed earlier. There are certain situations in which the departure volume will not give you an accurate representation of the actual demand of the intersection. So if you have a normal queue, 5-10 vehicles, and so when you stop your study, there are 5-10 vehicles which are still in the queue, you may have an error of 5 to 10 vehicles, which is not much. And considering the fact that you may have counted extra 5-10 vehicles at the start of your study, which was the queue from the previous hour, this error is compensated, mostly compensated. But when you have a very long queue and you count the vehicles which are crossing the stop line, so you may have counted 100, but there are 100 which are still stuck in the queue. So now you can imagine your error goes in hundreds. Okay, so to avoid this, then we try to find out the arrival volume, which means the volume which is coming and joining the queue, not the volume which is leaving the stop line. First thing we need to decide is which situation will require arrival volume, which one will require departure volume. So for arrival volume, if you have a signalized intersection and you have an overflow condition, overflow meaning that the flow from the previous red is still there in the next red, so people don't leave in the immediate green time. Okay, so when people are waiting for more than one red interval, this is an indication of overflow, and then you need arrival volume. Another indication is for unsignalized intersections. So for unsignalized intersections, you want to decide whether you should take arrival or departure. Then you go there, wait for a couple of minutes, count number of vehicles in the queue few times in those couple of minutes, and see if the count is increasing. That means that the queue is building up, and then you should take arrival volume. Okay, so you counted now, it's 5 vehicles. You counted after a minute, now it's 10 vehicles. You counted after another minute, and now it's 13, 14, 15 vehicles. So you see the count is increasing. So that means it's a queue build up, and you need arrival volume in that case. So once you satisfy any of these conditions, then you should take arrival volume. But the problem with arrival volume is in the queue. It's in the queue, and the queue itself is moving. It's not a fixed point. Okay, it moves forward and backward and stays and then moves and so on. So it's complicated to get the number in the queue. So what do? We use this equation, which you can see on the slide, to find out the arrival volume. So what are we using in the equation? VAI means vehicles arrive during time interval I. Okay, VDI, which is volume departed during time interval I. Departed is the volume which is going from the stop line. So you will still count the volume on the stop line, which is a fixed point. It's a fixed point of the observation. Stop line doesn't move. So I make my life easier. Then I have NQI. NQI means the number of vehicles in the queue at the end of time interval I. At the end only. So it's not like you have to count it through the time interval every minute. No, you just do it at the end. And NQI minus 1 is number of vehicles in the queue before the time interval I. Okay, so at the end and at the start basically. Let us look at an example. So you can see here we have volume count, which is vehicle departed, and the queue, which is done after every 15 minutes for 2 hours. So if you look at the first 15 minutes, 50 vehicles departed, nobody in the queue. We don't have the previous queue count. That means 50 have arrived. Next, same thing, 55, nobody in the queue now, nobody was in the queue before, so 55 have arrived. Then we have 62 who have arrived, or who have departed. And how many arrived? 62? No, because when we finished at 4:45 and we looked at the queue, there are already 5 vehicles in the queue. So actually 62 plus 5 arrived. Okay, 62 plus 5 arrived, and then total is 67. Okay, next one. So we have 65 which departed and 10 are in the queue. So should I say 75? No, because the queue was already up to 5 vehicles before. So it is 65 plus 10 minus 5. Okay, so 70 vehicles basically arrived, and so on and so forth. So you can do the calculations yourself and refer to the equation. Okay, so what I told you is just following the equation. Okay, now you can see here the queue count initially was 0, final is also 0. So that means the total arrived has become equal to total departed. So if you, when you calculate the arrivals and you do the total, then you will get 469 there as well. Okay, because there was no queue before, so no vehicles from the back period, and now no queue as well, so nobody who arrived has not left. Okay, so the total will be equal. Some more considerations for the signalized intersections. So at signalized intersection, we have the advantage that observers can look at different movements in different times, because movements have their specific signal timing. So I can say to this, to observer A, okay, count this particular movement now because it has green now, and when this one will have red, that other movement will start having green. So you do these two movements together. Not together, like you have to do it yourself, because they are not happening together. So this is our advantage. We can assign more movements to the same observer. Okay, another thing which you have to keep in mind is the cycle length of the signal. What is the cycle length? The time taken from the start of one red to the start of the next red. This is called as one cycle, and the time taken for that is called as cycle length. So on signalized intersections, you have to keep in mind that your counting period and the break period. I already told you that the manual counting need breaks as well. So counting period and the break period should be a multiple of cycle length, or the cycle length should be a multiple of these periods. So if you are having a cycle length of 2 minutes, so you cannot make counting period of 15 minutes. Okay, or you cannot take a break of 1 minute, because the cycle length is not multiple of these values. 2 minute cycle length means you can make counting for 10 minutes, a 2 minute break is fine, or 20 minutes and 2 minutes break, fine, but it should be a multiple. Cycle length should be a multiple of counting and break period. Okay, and obviously if counting is, if cycle length is multiple of counting and cycle length is also multiple of break, then if you add them together, then cycle length is a multiple of the total as well. Okay, so 10 counting, 2 minutes break, total is 12. So if cycle length was multiple of 10 and multiple of 2, that means it is also multiple of the total as well. Total is 12, which is multiple of 2 minutes. Okay, so your counting period and break period should be a multiple of the cycle length. Okay, now the problem, now why are we doing this? First of all, why we are saying that it should be multiple? We are saying this because to have equal chances to every movement within your counting period. So for example, the cycle length is 2 minutes, you count for 15 minutes. It's not a multiple of 2. So what will happen? In 14 minutes, you will have 7 cycles. That means 7 times each movement had the green. In the last minute, some movements will have the green, the others will not have green at all. So in that last minute, you may you may see more volume from a particular site because it had the green, and your data shows it has more volume, not because the actual volume is more, but maybe because it had more chance. So if you waited for the extra minute to complete the cycle length, so other movement may have the green, and that movement may actually have more volume. Okay, so this is the theory behind it. That's all movements should have equal chances at green and yellow, so that we know which volume is actually higher without the bias of the number of times the signal is becoming green. Now there are some signals which are actuated, meaning they are connected to the sensors. So they operate according to the sensor data. And sensor data catches more volume from one side, it increases the signal timing of that side. So signal timing is changing, that means there's no constant cycle length. So what should I do in that case? Then we take the maximum cycle length, and the maximum cycle length is set by the programmer of the signal. So the signal can increase the time, but it will never go above this maximum value. Let's say the maximum value is 3 minutes. Then you can keep the counting period and the break period as a multiple of 3 minutes. Okay, and they have mentioned here that the counting period should be at least 5 times of the cycle length. Okay, the maximum cycle length. But any value should be a multiple of the maximum cycle length, because now there is no cycle length here. No constant value of cycle length here. So we just rely on the multiple of maximum to fix our value. Now the same problem may happen which we were discussing for the non-actuated signals, that you are working on maximum cycle length and the actual cycle length is less. For example, maximum cycle length is 3 minutes. Actual cycle length is 2 minutes. You took a multiple of 3, which was 15 minutes, which is fine. But actually what is happening? The actual cycle length is 2 minutes. You didn't know. So again, you will have 7 complete cycles and 1 half cycle. Okay. So that in that 1 extra minute, some some directions will show more volume. So what is the answer to that? The answer to that is the sensor. The signal timing is changing according to the volume because of the sensor. So if you see a direction getting more chances at green, that also means that it has more volume as well. Okay, so more chances of green are because of the volume now in that case. Okay, so we don't have to worry about it. We just have to worry about how much time of counting should be fixed, and for that we will use the maximum cycle length. So this is it, then we'll continue next time inshallah.